Hello. Hi guys, good morning. Welcome back to a new video. In this frequency problem, sum of sub-array minimums, and oh god, it has been asked by Amazon, Adobe, Microsoft, Dunzo, and PhonePe. It's not at all a media problem. So yeah, let's start with this. Disclaimer, cool. But yeah, we'll see the entire intuition. No worries at all. Just sit back and relax. So we are given an array of integers, ARR, array of integers. Find the sum of minimum b where b ranges over every continuous sub array of ARR. So basically we have to know every sub array of ARR. For that every sub array of ARR, we need to find the minimum element of that sub array and then add that to our sum and get that sum. What we mean by that example is, for let's take the first example and we will do exactly what the question says. We have given the array ARR, we will go on to all of its sub array. So as usual, how we go on to all these sub arrays, I'll start from, let's say 3, I'll go to 3, 3, 1, 3, 1, 2, 3, 1, 2, 4, and then I'll start off with 1, 1, 1, 2, 1, 2, 4, then start off with 2, okay, 2, 2, 4, and then start off with 4, okay, ultimately a 4. So basically, okay, you are at I, you will start your j from I up till the n. You are at next I, which is this next I, you'll start from your j, like from this I up till the n. Okay, now you're at this I, you'll start off your I from like your j from this I up till the n, and so on. You will keep on going, but your task was just to figure out the minimum element. So okay, you will get all these sub arrays of n square time, but for every sub array you have to get the minimum element, which will take again O of n time. So basically you will take O of n cube time to solve it, which is for sure very bad. So you will try to optimize it. Now while doing or while going on the sub array itself, why can't you maintain the minimum? So rather than taking this O of n extra time, I'll parallelly maintain the minimum itself. So as I do a simple for loop, earlier what I was doing was, okay, I was doing, okay, I, j, and then after that I'll put another loop, let's say for int k is equals to I, k is less than equal to j, and k plus plus, and then find the minimum. This is earlier in n cube I was doing. Now I know, okay, it's not required to actually make this another loop for figuring out the minimum value. I know I am starting from 3. I can keep on maintaining the minimum. Okay, if 3 has a minimum of 3, okay, 3, 1 will have a minimum of 1, then 3, 1, 2, 1 and a minimum of 2. So basically I am keeping track of what is the minimum so far, and the incoming element, just get that minimum. Okay, minimum so far up till 3 is actually only 3. 3, 1, okay, 3 was the minimum so far, now 1 came, now it is a 1. 3, 1, 2, minimum so far was 1, now a 2 came, still the minimum is 1. 3, 1, 2, 4, minimum so far was 1, now a 4 came, so the minimum is again a 1. So that's how I'll keep on maintaining the minimum value, and as I am propagating through my j itself, I will keep on updating my minimum value with the existing minimum value to the current AR of j, and that's how I can simply get the minimum value at every point of time and keep on updating that. So with this you will see that, okay, you will reduce to O of n square time, which is still very high. Now how to actually solve this? The best thing is to think of the intuition that, okay, what data structure we can apply. Let's think of XYZ data structure is going to be applied. We don't know anything at all about that. It's just that we will see how the things are happening. If we plot on that how what we did earlier, what O of n square thing was doing, it was going on to all the sub arrays. Okay, so basically like you can either go right side or you can also go left side like this, 1 1 1 2 1 1 2 1 2 1 2 3, like this. You can go both sides, right? So let's take that, okay, it was a 3, one, like another was a 1 and 1 3, you can see 1 and 1 3, another was a 2 2, a 2 1 and a 2 1 3, which you can see here, another was a 4 4 2 4 2 1 and 4 2 1 3, 4 4 2 4 2 1 4 2 1 3. Now you will see that if I just see the minimum, because ultimately I'm concerned about the minimum only. So if I see the minimum, okay, for 3 the minimum is 3, for 1 it's 1, for 3 1 it's 1, for 2 it's 2, for 1 2 it's 1, for 3 1 2 it's 1, for 4 it's 4, for 2 4 it's 2, for 1 2 4 it's 1, for 3 1 2 4 it's 1. These are the minimum values, and that's what I wanted. So I'll just simply add these values in my answer. So if I simply write this down, my 3 is coming only one time, which is only this. My 1 is coming 6 times. 1, 2, 3, 4, 5, 6. 6 times. My 2 is coming 1, 2. Only 2 times. And my 4 is coming just one time. So I can simply add the contribution of each element, and that's how I'll get my answer as 17. So, okay. We got to know, Aryan, we got to know one thing, that we are adding the contribution of each element. Oh. And that's ultimately this entire thing was doing. So can't we do one thing? Can't we just figure out the contribution of each element in O of n time? Which means for each element, if I can get the contribution O of 1 time, that's great. Now, to know the contribution of each element, you will have to see that, okay, it should be the minimum element of that specific subarray. So now I know one thing, okay, I will just need to make sure that, okay, I need to get 3's contribution. So 3's contribution can only come when he is the minimum in his subarray which I am trying to make him. So, okay, 3 is here. 3 can try to expand on both sides, left and right, so as to make all the possible subarrays. But he knows left there is nothing, right is a smaller value, so he cannot expand, because if smaller value came in picture, that 1 will become small. But I'm trying to find the contribution of 3 itself. So for 3 is just 1. Okay, great. For 1 he can stay alone. Okay, for 1 he can, if I just write it with a different color, so for 1 he can stay alone. 1 can pair with 3 in the left, 1 can pair with 2 in the right, 1 can pair with 2, 1, 2, 4 in the right, because see, 1 is being the minimum in all the possible subarrays which I am trying to make. So for sure 1 will be added in the contribution, and 1 can also come in like 3, 1, 2 as a subarray. 1 can also come in this. So these are all the possible arrays in which 1 is present, and for sure 1 will contribute in the answer because he is the minimum out of all of them, like out of all the elements which are present in the subarray. So we will see that, okay, how to actually expand. But right now you might have get the intuition, okay, I have an element, I want to find its contribution in the answer, and that I need to get in O of 1 time, or basically O of log n time, because I want the complexity to be O of n or O of n log n, because I want to reduce from O of n square. So now if I know, okay, it has to be O of 1 time or O of log n time for every element, which means that, okay, this is the element right here which needs to be the minimum. So I just need to get, okay, anyone in the left or anyone in the right should not be lesser than me. If I can, I'll keep on expanding until everyone is more than me. If anyone comes lesser than me, I'll stop. If anyone comes less than me, I'll stop. That's what is in my mind. So you right now might have seen, okay, I want something. As soon as a small element came in left, just a small element it came in left, I'll stop. Just small element came in right, I'll stop. That's what I know, that, okay, I'm gonna stop at these points. Now coming on back, let's say if I try to expand 2, okay, 2 can be there. 2 cannot expand in the left because a smaller element came in, and as a smaller element will come in, he will try contribute adding the answer. But now right now I just wanted what is the contribution of 2. So 2 can only expand on the right. Okay, great. 4, he cannot expand on the right because nothing is there. Expand in the left, 2, which is smaller. If 2 came in, for sure answer contributing the 2 and not the 4. So that's what we know. Okay, we are finding the contribution of every element, and we are making sure that we want the minimum. So we will want to expand in the left and in the right such that no other smaller element will come in. So I'm concerned about the nearest smaller element in the left. For, as you remembered, for 2, nearest smaller element, either the end, that's okay, or nearest smaller element in the left and nearest smaller element in the right. So that is what I'm concerned about. For 1, okay, nearest smaller element, nothing was there. For this, nothing was there. For 3, nearest smaller element was actually at the 1 itself. For 2, it is here and it is nothing. For 4, it is in the left. So I'm only concerned about nearest smaller element to the left and nearest smaller element to the right, because I know that as soon as I get a smaller element, I have to stop, because else he will start contributing and I would not. And I want, okay, if I am at ith index, I should contribute, only I should contribute. So that's what I wanted to know. Okay, if I am at 2, I'll keep on going in the left. Okay, I'll keep on going in the left and I'll keep on going in the right until I find someone smaller. So I know, okay, my 2 can contribute in all the subarrays. Okay, like my 2 can have all the left elements as 2, 3, 4, and
like he can have all the right elements as 2, 6, 4, 3. As soon as 1 will come, which means any just smaller element, any smaller element than 2, as soon as it comes, I have to stop, because I cannot go beyond that. Because if I start going beyond it, my 1 will be added in the answer. Like my 1 will become the minimum value, but I want the contribution of 2 right now because I'm standing at 2. Now, by the naive way, to get the minimum to the left and minimum to the right, like just smaller in the left and just smaller in the right, naive way, you will actually start iterating O of n on the left and again O of n in the right. So for every element you have to do that, because it is the correct ith index. You'll have to do for every index, right? For every element, if you will keep on performing O of n, that will again become a O of n square. So that's again a task for us, that okay, I want minimum to the left, minimum to the right, but that's again gonna be O of n square. So that's where, if you have heard of monotonic stack, or finding the nearest smaller element in the left, nearest smaller element in the right, nearest larger element to the left, nearest larger element to the right, finding the indexes of them, finding the count of them, like how much is the range of them, all this is done by monotonic stack. Just remember this. If you are in the very beginning phase, if you have not solved any problem, just remember this phrase. If you want to find nearest smaller, nearest larger element to the left or to the right, again, it can be an index of the element, it can be the frequency of the element, as in like how many elements are there, it can be that how much is the length of the element, you can use monotonic stack. How we use it, we will see that. But yeah, in this we actually use stacks. But that one thing is still missing, that okay, even if we get the count of left elements, as you can see, it is actually left elements, after 2 left elements are actually 2, and after 2 left elements are actually 3, sorry, right elements are actually 3. So how many number of sub arrays would 3 be contributing, or basically would the element 2 be contributing? That's still a question, because if you just go back and see that okay, in the left I had just 1 element, in the right I had 2 elements, but the contribution was actually a 6. Because of 1, the contribution, obviously some number of sub arrays which 1 was contributing was actually a 6. So that's gonna be a task, that how are we gonna do that? For that, just a simple visualization, that okay, if I know okay, from 1 number of left elements are 2, from 1 number of right elements are 3. So if I know okay, by visually my number of sub arrays my 1 was contributing answer to was actually a 6. So I can by default, by assumption, say that okay, it is left into right. But again, Aryan, how, as in why? So for that, the basic thing is that okay, if I just try to replicate the number of sub arrays, what could have been there? So okay, I'll just remove this, I'll just remove entire thing, and I'll say okay, this is the right part, it can form one entire array, the left part is this. Now in the left part, either I take this one, 3, or nothing. So I can say okay, either on the left part I have, let's say the left size is 1, right? But I'll take it as a 1 plus 1. Let's say if the left size would have been, let's say if one more element would have been there, let's say 2, or like 2 would have been there, so let's say left size would have been a 2. So I would have taken like left size plus 1, which is whatsoever elements are there plus 1 as an empty element, as in nothing. How and why it is required? Because I'll say okay, I will pair nothing with the all the possible in the right, I'll pair 3 with all the possible in the right. What I mean by that is that okay, I'll pair my 3 with 1, 3, 1, 3, 1, 2, 3, 1, 2, 4, 3, 1, 2, 3, 1, 2, 4. That's gonna build my actual sub array. Or let's say if I take nothing, 1, nothing, 1, nothing, 1, 2, nothing, 1, 2, 4, nothing, 1 to 4, and that's how you're gonna build your 6 sub arrays. That's gonna be your answer. So what if Aryan, it would have been a 2? Okay, if it would have been a 2, then I would have said okay, 2, 3, and then 1, 2, 3, 1, 2, 2, 3, 1, 2, 3, 1, 2, 4, sorry. So that's gonna say that okay, number of elements in the left, which are actually here, you will see it was number of elements in the left were actually here 2. So I'll just say 2 plus 1, 2 plus 1. Now 1, although I am actually overlapping with this specific one, but this 2 plus 1, when I say 2 plus 1, 1 is nothing but the empty, and right in the right I have again number of right elements, which are actually nothing but right elements. So that will say left multiplied by right will give me the number of subarrays in which that element will be contributing in the answer. Okay, so I have known just one thing, that I'll just erase this. I will know, okay, I will count my left as including the element, right as including the element. Now if you remembered, left is including, which means it is already having an extra value, which is 1 itself. But actually in our mind we know, instead of 1, while building the subarray, we will actually like assume it as an empty subarray, right? So as to build the all possible subarrays. So I know, okay, if I have the left count, which is nothing but 2 here, I have the right count, which is nothing but 3 here, I'll simply multiply that, because I know by simple multiplication I can get the answer. So okay, we can get now our main aim is to find the number of elements to the left, number of elements to the right, such that it is not passing the nearest smallest element. So now comes on that first small element to the left, first small element to the right. That's what we're gonna find, and with that we're gonna find, okay, what is the range, or basically what's the count of elements. So if we come back to the normal example, ARR, for this 3, you will see I just wanted the number of elements to the left, right? As soon as a small element come in. For 3, okay, one element is himself, and then he cannot go back, so answer is 1. For 1, he is the one element, he can try to go left also, but he cannot go left beyond this. Okay, so for 1 the answer is 2. For 2, he is one element, okay, he cannot go 1, okay, so he will stay 1, okay, answer is 1. For 4, he will be one element, that's great. He cannot increase to 2, okay, so the answer is 4. For 4, answer is 1. Again, for the right, if I go back, for 4, he cannot go right, okay, so the answer is 1. For 2, one element for is 2, he can go right also, because 4 is larger than 2, so for sure the answer for 2 will be 2. For 1, he can be one element, okay, sorry, for 1 he can be one element, he can expand in the right, because 1 is smaller than 2, 4, so he can expand on the right, okay, his count will be a 3. For 3, okay, he cannot expand because it's smaller, so he cannot expand, so his count will be 1. So this is what we have to build. But remember, this is what we have to build in O of n time entirely, which means for all the elements it should be built in O of n time. We cannot use O of n squared to build this left and right, and that's where we're gonna use a stack. That's the reason, like you saw, it's strictly increasing, strictly decreasing. We'll try to, again, why is the name as monotonic stack? Because a stack will maintain the elements in the strictly increasing or strictly decreasing order. That is the reason, monotonic stack. Okay, let's see, let's try to build our left. So we know that, okay, this is the expected. Always while writing or while actually doing a contest, please write expected, what is expected, and then try to build your own stack. So what I'll do, okay, I know it's error of this. So first element is 3. Okay, simply push that element, right? Okay, I simply pushed it. I know that I'm pushing the element with a specific count. This is what I am pushing. So maintain that. Okay, for the left, answer is 1 so far. Remember this, whatsoever was written, I'm just erasing it and I'm writing the answer again. For 3, which is because I am at the current index I. So for him, I just put it in the stack. So answer is 1. Okay, now I am at text index 1. I'll keep on checking my stack and keep on adding its value, whatsoever I'll get. Okay, for 1, okay, 1 count is 1 itself. I'll check in the stack. Oh, stack had a 3, which is more than my current value, which is 1. So remove the index firstly. So okay, it is more than 1. So bro, please remove it. Okay, I'll simply do one thing. I'll simply remove it. If I'll remove this, I know, okay, this is the number of elements for which 3 was actually, like for 3 it's more, like 3 is less. So if 1 is also less, so I'll have to add the count of all the elements which are lesser than 3. So which are more than 3. So this maintains the count of elements on the left of 3 which are more than 3. So I'll just simply add the 1 in my specific 1. So now my 1's count will become a 2, which is representing that, okay, it's a 1, it's actually a 2. Okay, great. So it will be a 2. For 2, again, I will try to add it. I'll check if something in my stack is actually lesser. If something in the stack is actually less, then please don't touch it. If it is more, remove it and add its count. Okay, he will check in the stack. it's actually less. If something would have been more, as you can see, for 1 the 3 was actually more thing, so he removed 3, but 2 cannot remove 1, so 2 will actually add it. So okay, for 2 the count is right now a 1. Again go on to 4, that okay, for 4 he cannot remove 2 because it is less, he can only remove the more elements, so he will actually have a 4 1. So okay, for 4 also count as 1. Now this is one kind of variation of monotonic stack. Again, there can be multiple variations in which you might, again, you see that okay, why it is monotonic, because the values are always increasing. There can be variations also in which the values are always decreasing, so you will try to maintain a stack that is actually increasing or decreasing, and that's how you're gonna know that okay, it's a monotonic stack. Again, if we go back and see, it's ARR, it's right, we'll try to build it from the right itself. Okay, now I'm currently at this specific I, I'll simply push, it's the first element, nothing there, count is 1. Okay, simply push this, I'll go on to my this I. Okay, for sure my element 2 is actually more than the, sorry, it's actually less than the top of the stack, so for sure the thing which is already there is more, so simply remove it. I'll simply remove it, and I know I'll get this count which is 1. I simply add in my current one which is 1, so I'll get a 2. Okay, this is removed, I have got a 2 comma 2. I'll go on to next element, that will say okay, he 1 is actually lesser than the top of the stack, which is 2. Top of the stack is 2, he's less, so for sure the top will be removed and 1 will come in picture. Now 1 will come in picture, what should be added in its count? Its count, currently I have just 1 element and the top says I will have 2 elements for you, so I will just simply add a 1 is the element and count will be 3, which is nothing but this 2 plus 1, so it became a 3 as the count and added. That is the reason you remembered, right? Okay, this 2 represents I have 2 and bigger element in the right, so it is just a count saying that I have these number of elements bigger, so you should simply add 1 for yourself and the count you will take from me itself. Okay, great. For 1 I have added the count, so that's a 3 updated here. Then I will come here, for sure it is more than my 1, so I'll simply add a 3 comma 1, and you will see again it is a monotonically increasing stack. Again, I'm saying just a monotonic stack, which means it can be increasing and decreasing both, or decreasing both, right? So that is how you can simply build. And again, you just went on to all the elements exactly once, and in worst case you might be removing all the elements, so you are just going on all of the elements exactly twice, at max twice. That is what you are doing. So your answer will be O of n to generate this right array, O of n to generate this left array. That's how you will generate this left and right array. And when you have generated the left and right arrays, you know that simply for every element, let's say for this ith index, I know the left count is 2, right count is 3. So for every element, just simply okay, I want the contribution of that element, so simply multiply AR of I multiplied by left of I multiplied by right of I. That is the contribution of that specific element, and repeat this for all of the elements or all of the indexes, because you know you have to go on to all of the indexes, and that's how you can simply get the answer. There's just one edge case which is there. What if the elements are repeating? That is a slightly edgy case, for sure, edgy case, that okay, if you have duplicate values, then you don't want the things to be repeating, which means that okay, as you remembered via a very brute force, if you are standing here, okay, this is 2 is one element, 2 is another sub array, next 2 is another sub array. So this 2, okay, this 2 and this 2, these are all the possible sub arrays of this problem. Now minimum you will see is it's always 2. So you can see that okay, for this 2 the contribution is 2 into 2, 2 is the element and 2 is the count. For this 2 the contribution is 2 into 1. So I have to make sure that I am actually counting for all the contributions of a value. So, and I don't want to do a double counting also. So I will make sure okay, while doing a left, I will not include the equal elements, but while doing the right, I will include the equal elements also, so as to not do a double counting. What we mean by that is, let's say if I'm building the left itself, okay, 2 came in the picture, the first 2 came in the picture. Let's say if I erase this, so first 2 came in the picture, 2 comma 1, okay, first element, so the element is value 1. Next 2 came in the picture, again next 2 came in the picture, so you will just simply say 2 comma 1. If an element would have been larger then you would have removed it. But if it is equal also, still, if it is equal or less, you will not remove it. Here, while building the left, I did not remove the equal elements. So as, okay, right now I am saying, okay, left, he will not go back. He will not go back. For him, okay, the value is 1 because he's trying to go left. Okay, but I am for this element, I'll make sure, okay, he should not go left because I want, okay, I can just try. See why I am not moving left here, because while building this, I will move right. So if while building this, I am moving right, which is like this. See, if I am standing here while building a right, if I will move, it will form a 2-2 like this. If I am standing here while building a left, if I move, it will form like this. So this, you can see, it is actually repeating. That's what I don't want. So I'll just simply move in one direction. In, let's say, if I'll move only in the right, I'll move only in the left. That's what I'm gonna do. So I know that, okay, if I'm standing here, I'll be here. I'll not try to move. Even if it's equal, I'll not move on the right. I'll move only when it actually I encounter a higher value. That, okay, if I'm here, that he will try, he will try to move on the left part, but he cannot because he wanted to actually encounter only the higher values. Now coming on and building the right part. Okay, for right, he will actually just go right. Element also itself is finished. But while building the right itself here for 2, he will check the top of the stack. If it is equal or more, then he can remove it. Okay, I'll remove that from the top of the stack, and I'll increase the count of this specific to a 2. So by this, you will avoid double counting, because in the left, you are only checking for greater than values. For right, you are only checking for greater than equal to values. So now here, equal to will come in picture. Equal to should only come in picture in one of them, either left or right, so as to avoid double counting of 1. And that's gonna be your answer. Cool. So this is the one thing which you have to make sure. I show that in the code also. Now the code is pretty simple. We will simply have to make a left and the right vectors as we saw above. These left and the right vectors, these left, and these right vectors we have to simply make, because if you remember, this is the left and right which are actually useful for us. Left and right vectors which are actually useful for us. So if we go back, and this will be the stack, simply stack of pair of in comma int. Pair, which means this element, this first is the element, this next is the count of the elements which are actually higher than or equal to me. Well, again, 1 will be added for sure, and this will say higher for left, and for right it will be higher or equal. Cool. As we saw, so as to avoid double counting. Now I'll go on to all the elements of the array, and I will try to build my left. I'll try to build my left array. Pre-computing again. So firstly, for every element, he will always be the count. For every element, he will always be there as the count. Now, and if my stack is not empty, Aryan, why that stack is not empty used? Stack is not empty is used so that you don't pop, or so that you don't try to access an element which is not even there. So you will try to access the element which is even there only when the stack is not empty. So if the stack is not empty, so you will try to access the top element. If the top element, if it's actually its value, see, first is nothing but the element value itself, and second is the count of that value. If the first it's more, if the top element value is more to the incoming element is air of I, then you will remove that element, which we saw. It was a 3-1, then 1 was coming in as a air of I, then we removed this 3 and added a 1 comma 2. 2 is nothing but the count of this specific thing, and added a 1 on top of it. So I'll simply increase, and I'll keep on increasing the count. If I have multiple elements in the bottom, I'll keep on increasing. I'll keep on removing those elements. So if I have a count, I'll simply add, okay, whatsoever is the stack which was the top element, just remove that, and add its count value in this count, which was initialized with 1. So I'll keep on adding the count value, and then simply pop it from the stack. And again, when you have done the entire thing of popping for that specific incoming element, now you know that you have to push that element to the stack also. So you push the element and the count. So I push the element and the count. And again, like when this entire thing is done, you can simply update your left also, because this left is ultimately which you want to use in your answer. Stack is just to build or just to know the count. That's it. Now the exact same thing I will repeat for my right. Exact same thing. You will see exact same thing. It's just that I'll move it from the right itself. So I moved in from the right. So as you can see, moving from the right, exact same count, exact same trying to see if the stack is not empty. If the stack top is more than equal to, so like you remember, more than equal to is just to make sure that, okay, above I put more than, here I put more than equal to, so as not to do a double counting or not to miss. If I did a equal to at both the places, then I would have missed the equal values. If I would have put equal to in both the places, then actually I would have double counted those same values. So it's the reason at one place it's greater than, at one place it's greater than equal to. Now simply exact same stuff, that add its count corresponding which you're removing, remove that from the stack and keep on doing it if you have a higher value in the bottom of the stack. And ultimately when everything is removed, simply push the current element and its corresponding count and simply update the right also. When the entire thing is done, we know that the contribution of any answer is nothing but left multiplied by right multiplied by answer. And please do a mod at every point, that's so that you don't overbound, or basically so that you don't increase your integer limit and ultimately return the answer. And that's how you're going to solve an O of n time in O of n space. I hope that you got it. Goodbye, take care, bye bye. I know it's a long video, but yeah, that's actually a hard problem. Bye.